Hey folks, welcome back to our second to last unit of 2020 and distance learning. Hope you're all doing well and hope that you were able to get the electricity exam done yesterday. It does allow you to do a retake, so if you aren't satisfied with your score, you can try it for a second time. There is only two tries, but know that that is the option. That is an option for you. Our next unit, as you might gather by the headline here, is about magnetism. And hopefully by the end of this unit, we're going to have a really good feel for how magnetism and electricity are tied together. And as we start diving into a little more of the uses of magnetism, because a lot of us, we don't realize how much we use magnetism. We think we maybe stick things on the refrigerator, and we know that they're good for that purpose. But there's a whole lot more to it, and hopefully we can make some sense out of that. There's both attraction and repulsion, and they're critical in, well, our everyday lives. Today, I'm hoping to tackle really four main terms to kind of have under our belt moving forward. Some of which I think you probably are going to be pretty familiar with, but there might be one or two that is going to look a little newer to you. Magnetic poles, magnetic force, magnetic fields, and something called magnetic domains today are what we're shooting for. Now, when we think of magnetism, I think the definition probably is pretty typical for what many of you understand. The force of attraction between opposite magnetic poles and the repulsion between like poles. Now, magnetic poles happen to be where that magnetic force is the strongest. That's where we're going to see in some diagrams here in a little bit where the magnetic field lines build up. We use north and south when we talk about magnetism, not positive and negative like we did in electricity. Although there is going to be kind of a tie in a little bit in how some of that comes into play. But north and south poles, so a little different terminology, a little different meaning there when we talk about the opposites attract and the likes repel. And that, again, holds true just in magnetism, just like it did in electricity. Opposites will pull together, likes will push apart, and that's what we call the magnetic force. So here we can see the effect of like and opposite poles when they get near each other. I've got a couple of donut magnets and a graduated cylinder here. And if I hold the one side down, drop it in there, they latch together really well and they're strongly attracted. If I pull this off though, and I take that magnet and I flip it around upside down, now I bring it down and you can tell that the like poles are near each other. And so they're going to repel. A donut magnet does not want to attach. If I bring a separate bar magnet in, if I bring the south side near this one, you're going to see how it attracts to it. It's going to pull it up. If I flip it around, however, bring the north pole down, it doesn't want to go towards it anymore. It's repelled away. I flip it over and they snap together. Now, just like we learned with electricity, magnetism can reach out through space and affect things. What we call the magnetic field is the area surrounding a magnet where those magnetic forces affect things, where they act. We already mentioned that they are strongest at the poles. That's where these, what we call magnetic field lines, bunch up. As you look at a couple of the diagrams there, you can see that there are all kinds of the lines going off from the poles. And you'll notice the lines have little arrows. Those field lines will run from north to south. So we've already become familiar a little bit with how that magnetic field can reach out through space and affect things, how it keeps the magnets repelled from each other. In this next little demonstration that I have put together here, we're going to see the magnetic field lines being given off. If we zoom in a little bit, it's a little tricky to see, but you'll see kind of the iron filings that are in there that are surrounding this magnet that's suspended in mineral oil. And you can kind of see some of the field lines as they move away from the magnets that's suspended in the bottle. And you'll see that they obviously clump up at either end where the poles are, and that's where, of course, the magnetic field is the strongest. Well, you might be wondering, well, what causes magnets to happen in the first place? And it's an excellent question, and it's something that can be a little tricky to understand, but we'll try to keep it simple for us and make sure that we're on the right track and not get too crazy. But in a word, what causes magnetism to happen is moving electrons. And when an electron moves, when it flies, what happens is it gives off a magnetic field. Anytime we have moving electrons, it causes little fields of magnetism to be formed, and we'll show that in more detail later. And it was a very critical discovery that took place. And you might say, well, don't all atoms have moving electrons? And the answer is yes. But here's the deal. In most things, the magnetic fields that form because of the moving electrons essentially are going in all different directions, and they cancel each other out. And the net result is that there's really no magnetism there at all because it really is all canceled out. There are a few elements, however, that happen to have some what we call unpaired electrons, and they can align their small magnetic fields into stronger magnetic fields we call magnetic domains. Essentially, when those electrons are moving, they're creating small little magnetic fields. And in certain materials, their chemistry and their design is such that those can build up on top of one another, and they can align and build stronger little areas of magnetism we call magnetic domains. And that's why there are kind of three elements generally we think of that can form what we call permanent magnets, or what we call ferromagnetic materials. They're iron, nickel, and cobalt. Now that doesn't mean that they're always magnets. But they can be magnetized, and they can have those little areas of magnetic domains align. Now, when you break a magnet in half, because magnetic domains are little areas of both north and south poles, if you break a magnet in half, essentially all what happens is you just end up with two smaller magnets. You can't ever just break a magnet off and have a north pole and then the other half be a south pole. It doesn't work that way because it's all these areas of magnetism that are all put together. It's not just one end and the other end. All right, so a quick summary of what we covered. We learned about magnetic force, the attraction and repulsion between opposite and like poles. I think most of us were pretty familiar with that moving in. We also talked about the magnetic force is the strongest at those poles. That's where those magnetic field lines build up. The magnetic field, of course, is the area around the magnet that gets affected by that magnetism. And lastly, those magnetic domains are these little areas in certain materials where the magnetic fields line themselves up with the north and south poles going the same way, and it allows them to hold their magnetism. Time to do your quick quiz, and we'll see you tomorrow.